Okay, friends, we have great pleasure to welcome Professor Gourab Ghosal from University of Rochester as guest speaker. In the statistical physics physicist works in general in the complex systems and complex systems and statistical physics. So let me read out first a little biography for Professor Ghosal. Professor Ghosal, Gourab Ghosal is an associate professor in the physics and astronomy department with the joint appointments at the departments of computer science and mathematics. Professor Ghosal got his bachelor's and master's degree at the University of London, UK. He did his BS and MSc in theoretical physics in 2004. He did his doctoral thesis work at the University of Michigan, Ann Arbor, PhD in physics, 2009. Following his PhD, he was a postdoctoral scientist jointly at Northeastern University and Harvard Medical School, as well as a visiting scientist at the Media Lab MIT till 2012. Before joining Rochester in 2015, he was a research scientist for 3 years at the Department of Arts and Planetary Sciences at Harvard University and a member of Harvard's Multidisciplinary Origins of Life Initiative. His brief research overview is the following. Professor Ghosal is trained as a statistical physicist and works in the field of complex systems. His research interests are in the theory and applications of complex networks, as well as non-equivalent statistical physics, game theory, econophysics, dynamical systems, and the origins of life. He is the editor of a book on complex networks published by Scribbler, and his work has been published in Nature, Science, and Physical Review letters. Today, Professor Ghosal will be speaking on the topic of a physics approach to study urban system. Professor Ghosal.
Can you hear me? Is the sound fine?
Yeah.
Yeah, it's perfect. Okay, fantastic. So thank you very much, Professor Manna, for the wonderful introduction. And I'm very happy to be here at the SN Post Institute. It's a real pleasure. I've always been meaning to come for quite some time. I'm happy I've had the opportunity to do so. Today, I want to tell you a little bit about a slightly unusual topic, something which you might not be that familiar with, which is a physics approach to studying urban systems. It's somewhat non-traditional, but as I hope to convince you that I think it's a fairly important thing to study, and physicists have a lot to offer in terms of understanding the problems over here. Given the audience and given the sheer volume of stuff that's that's been done in this field, my plan today is to give you all a very high-level overview of selected bits of topics from that encompasses this particular field. And then at any point of time, if you want to go into detail, I'll be happy to do so, either during the talk or after the talk. So let me first motivate this problem. Like, why would one study this in the first place? Right? And let me do this by this this graph here. This was released by the United Nations. It's already a little bit outdated. But essentially, what it's showing is the state of urbanization, number of people who live in urban centers at 3 different epochs, right? So you have 1950 in from here, 2007, and then projected for 2030. So you can see basically about like 70 years ago, only about 1 in 3 people lived in cities. Currently, it's a little bit more than half, and then just less than a decade, it's projected to be about 60%. And you can break this up in terms of like different regions of the world. But here are some interesting salient facts, and I'm just using the US as an example. You can see in about 1800, less than 4% of the population of the United States was living in cities. And in about 200 years later, it's almost 80%, so 8 out of 10. We reached this threshold about 10 years ago, where over half the world's people now live in cities. And it's projected to be about 3 in 4 people in about 30 years or so. And quite remarkably, every week, about 1 million people are being added to cities. And this is almost certainly underestimated. If you look at the growth in China, it's probably an order of magnitude more. So the point of the matter is that there is this incredible urban expansion, right? There is this explosion, and it's unprecedented in human history, and it's only been happening over the last 50 to 60 years, right? So very rapid pace. Now, why are we interested in this? Is because like that's where we happen to live, right? So if most of the world's people are living in cities, we need to understand why this is happening, if this is an optimal thing that's happening, and if it's optimal or not, how can we make it so? In simple terms, is how can we make it sustainable? And it's a question that relates to our very existence. Because if we live in areas and these areas kind of collapse, we also collapse as a species, right? So in some sense, without exaggeration, it's one of the most important questions of the 21st century. And as you can see, things are fairly saturated in Europe and North America, right? There's not much difference. But most of the world's people live in Asia, right? And it's about 40% right now, and it's probably an underestimate 50%. So there's a massive transfer of population that's going to this. Okay, so that's, I hopefully convinced you why this is an important topic to study. All right, so the first thing that I asked is why cities at all, right? The question one can ask is why do people live in urban centers? And one can make some hand-waving arguments about this, right? So, people typically move to cities because there are opportunities. There are economic opportunities, there are good jobs, there are good educational institutions like we have here, nice places to eat, like Six Ballygunge Place, right? There's theater, there's music, all kinds of stuff. There's a lot of attraction, but allied against that is the negative aspects, right? Which we all, I think one of the biggest things is the presence of pandemics and epidemics, right? Disease. There's a question of crime and mugging. There's a question of pollution, which we all know do very well in India, and so on and so forth, right? So you have these competing forces. You have the positives, the negatives, and somehow, for the moment, it seems to be that the positives are beating the negatives, and people are moving to cities. And obviously, new question. People have been thinking about this for about 100 years or so, possibly more. If you want to know more about this, there's this wonderful book by it's called Why Cities. And it sort of traces about the 6,000 years of urbanization, starting from the Mesopotamians, Mohenjo-daro, Harappa, and so on and so forth, Rome, Babylon, etc., to modern times. Anyway, so like I said, sociologists and urban theorists have been making this like hand-waving arguments as to why cities exist. And I've given you some examples of that. But as a physicist or people who work in more quantitative fields, you want some empirical evidence. So the first, it's difficult to say the first because we never know what's first, but at least the first, to my knowledge, of something that was evidence in a language that I understand and perhaps you would understand, is done by this paper from these physicists at Los Alamos that happen to be high energy theorists. So this is Louis Betancourt and Jeffrey West. And they published this paper in PNAS about like 15 years ago called Growth, Innovation, Scaling in the Face of Life in Cities. So what did they do? They did something quite interesting with data. And they collected data about cities at the population level, right? So about various facets. So things about like, creativity and, R&D, right? So there's patents, inventors, R&D employment, economic conditions like wages and bank deposits, GDP, infrastructure like electrical consumption, and also other things, the negative aspects that I mentioned, right? So at that time it was AIDS, but now it's very different, and the incidence of serious crimes.
How vital is defined?
I'll show you. So what they did was, next was they took these population level indicators, right, agglomerative indicators, and they plotted that as a function of the population. So here you have, in the horizontal axis, the population. On the vertical axis, you have these indicators, all of them, right? And this is on a logarithmic scale, log scale, with a straight line. So what you see is like a power law dependence, right? So each of these indicators, y of t, right, the time dependent, is a function of the population to some exponent beta, right? That's what it is. And there are three interesting things about this. So the first thing is that you notice that across all of these indicators, the range of beta is very tightly bound. The second most important thing is that it's not one, it's greater than one, right? So this is a scaling behavior. This is not linear scaling, it's what's called superlinear scaling, right? So here's your first evidence. So this is basically a multiplicative effect. So when you say that people, if you put people together in cities, good things happen, you see that it's not a, it's not like 1 + 1 = 2, but 1 + 1 = 2.5, right?
You have discarded two data points, 1.07 and 1.08, I guess.
I mean, these are all, this is massaging the data and so forth. You're right, absolutely. Exactly, yeah. So the 1.07 you can see and 1.08. So the 1.07 is interesting. This is an infrastructure thing, right? The other ones are infrastructure. So it turns out that the infrastructure, in fact, this was later found out in further studies to be actually less than 1. So when it comes to infrastructure, you have economies of scale, right? So you have sublinear scale. Whereas for these other things, which involves like people's interactions, you have superlinear scale. So absolutely.
But what is n?
N is population size.
But then how is superlinear? Exceed the y exceed n, right?
So y scales as n to a power which is greater than 1. So that's what I mean by superlinear, right? So if this was yn squared, so that's quadratic. It's not quadratic, it's y to the n to a 1.13, 1.14.
I'm saying it is greater than y n, right?
What's greater than n?
Y is greater than n.
I mean, there's a scale factor here, right? Which is not the same.
Concept of proportionality.
Yeah, I mean, there's a scale factor here which would like, sort of. Yeah.
Scale factor is constant.
It will depend on each of these things, right? So, for example, if the population is like,
scale factor is constant, so for eventually you get one n for which y will exceed n.
that's fine, and the GDP of a city exceeds the population, right?
Oh, I see.
So,
Gaurav,
yeah.
While calculating this population, is it the density you also calculating? Because sometimes that cities also expand.
Well, I'll show you in the next slide. Yeah. So there's an issue with the n itself, which I'll bring. But first, let me say what's interesting about this. So the first thing is that it's bound. Second is superlinear, right? Which is a multiplier effect, which tells you, for the first time, quantitatively speaking, you're getting these effects of like putting people together, both positive and negative, because it also applies to the disease and the crimes. The third thing, which is very interesting, is that this is true across all cities. Well, we qualify that all developed cities. Right? So here, this is being shown for US metropolitan areas. And if you want to do this for European cities, and specifically cities in the OECD, so Japan and so on and so forth, you would find the exact same scale. Right? I mean, this might be different, but the beta and this dependence are across all these places. So the question is, why is this happening? Because if you think about it, I mean, each of these cities have very different trajectories. They're in different locations, different geographies, different topological constraints, different political systems, but they all have this particular scaling. So why that might be the case? So this is what got me interested when I first saw this paper. And with some colleagues of mine at MIT when I was there, we kind of asked ourselves a very almost a naive question. Like, okay, we know what's not common among these cities, but what's common to these cities, right? And if you think about it, what's really common to these cities is that they're people. People live in these cities and people interact. So we came up with this very dumb and kind of naive model. It's typical spherical cow model, as I say in physics, where essentially we are saying that perhaps this scaling can be explained purely by the interactions among the populations. Forgetting for the moment about the infrastructure, forgetting for the moment about the topology and whatnot, because in some sense, they're averaged or integrated out because they're more or less at the same state in all these OECD cities. So the model is the following. Basically, you have some two-dimensional Euclidean plane, and it's very, very naive. And you seed them with like population density profiles. This could be Gaussian density profiles or whatever you want. Any distribution actually is agnostic to that. And then you define rules for how ties are formed between people, right? And the way we define this rule is based on proximity and the density. So the probability of forming ties is a function of how close people are, but also decreases as a function of how dense the density barrier you have to other people, right? So it's again a very simple thing. So when you have this model, you have this formation of these interesting spatial planar networks. Yeah. Yes, the spatial proximity. So it's a spatial proximity, but also density, right? So, for example, if somebody is about like a mile away or a kilometer away, but there's nobody there, that's equally probable to connect as opposed to somebody's half a kilometer away, but there's about 1,000 people in between.
And there is a no cutoff. It connects to as many as.
Yeah. Again, it's very nice. So you have these spatial networks that form, and then what you do is you simulate information diffusion upon them, right? So the speed of information spread, the speed of infection. And what you find is that you can reproduce this scaling behavior, this superlinear scaling behavior, where this actually goes as, this indicator goes as n log n. So it's superlinear, and actually it's not really n log n, it's rho log rho, it's the density. Because, there's a problem, there are equal amount of people in Siberia and somewhere else, but the densities are different. Right? So actually, it's rho log rho. So two things are nice about this. So one is that you do have these superlinear scaling, and the second thing is that you see over here you have this whole plethora of values, right? 1.27, 1.023. I mean, there's no rhyme or reason for these numbers. But if you actually try and fit a function to any of these, they actually look like that, right? So the n log n, right, is a straight line, but if you fit a polynomial function to it, it looks like 1.18 and so on. So in that sense, it is satisfactory. Having said that, again, it's very, very naive. It's a spherical power model. We threw a lot of information. So this just tells us that we're on the right track, that our guess that, that circling the interactions among people is driving this kind of behavior is perhaps the right way to think about it. But now we need to refine this. And to understand how to refine this, we have to first understand the limitations. Right? So the limitations of this model is, first of all, it's a growing network, but it's completely static because you're forming static links. And we know that's not how things work, right? People have different kinds of ties. They're moving all over the city. They're not just taking one place. So that's an obvious problem. And a variety of other things which are obvious in the limitations, but most importantly, the predictions fail because this superlinear scaling that you observe only happens in these advanced industrial cities. Whereas if you look at cities like sub-Saharan Africa and some of the more developing cities in Oceania and so on and so forth, you don't see this behavior, right? So what's happening is that you are not leveraging the multiplicative effect of putting people together. Okay. So now we take a step back and we say, let's build the model from the bottom up and put all these things back that we threw out, right? So the first thing you can ask is that, well, if it is indeed putting people together, which is giving you these positive benefits, then what is it that mediates interactions between people in cities, right? What is it that puts people together in the first place? So maybe one can explain the differences by saying that if you have an efficient system of putting people together, then you're leveraging this. And if it's not so efficient, then you're missing out on this stuff. And of course, let's not, I don't want to talk about like virtual interaction. That's not, that's a much later thing. We're talking about physical interactions. So the first approximation, there are many ways that people can interact in cities, but the thing that mediates it is really the street infrastructure, the city streets, right? So here is a nice picture. These are like 1 square mile samples of streets taken from different parts of the world, Canada and Spain and so on and so forth. And just looking at it visually, you can see, it's a nice picture, but also there are differences. The differences in terms of the isotropy of these streets. Some of them are very regular, some of them are anisotropic, some of them have these weird orientations, some of them are lattice, patchwork, and so on and so forth. So perhaps if one were to study the structural properties of these streets, one might explain, how one can leverage this benefit on one field. So there are many things that one can measure about these kind of streets. These are what are called planar graphs. So these are graphs that are embedded in some two-dimensional space. But since we're talking about the ease of putting people together or not, a logical thing to measure is the congestion properties, right? So in graph theory, congestion properties on a graph is measured by something which is called betweenness centrality. So just very roughly speaking, here is a cartoon that I made of a network, and the betweenness centrality of this particular junction street is basically the number of shortest paths that cross between this junction between any two parts of the network, right? So imagine if a bridge which connects two different parts of the city, that is a very high betweenness centrality because you have to cross that bridge to go from one part of the city to the other. On the other hand, if it's your driveway, then that's a junction, that's a terminal point, right? It's not in between any paths at all, so that has no congestion. So it's just basically a measure of congestion. So what one can do then is to look at, let's say, the 100 most populous cities in the world, taken from different parts of the continent, and download these street networks and just measure the congestion properties. The question is like, what do you get? Like perhaps there's a difference in some of these streets. So this is what you see. So this is just a histogram of this congestion distribution of the street networks of the 100 most populous cities in the world, right? So the horizontal axis is congestion. So if this is large, that means a lot of paths go to this particular point. If this is low, that means hardly any paths go to the point, right? So the first thing you notice is this is kind of like a right skew distribution, somewhat like a power law. So what this is saying is that, well, really most street intersections hardly have any congestion, whereas the majority of the load in cities lies at a backbone, right? A small number of intersections carry the majority of the load. Of course, there is this interesting, weird kink-like behavior. I won't get into it. There's some interesting analytical reasons for why that is. But if you look at this in a slightly different way, so if you account for the size of each of these cities, right? So, Vatican City is a lot smaller than Kolkata, right? So if I look at the street congestion properties of Vatican City and I look at Kolkata, but I account for the fact that Kolkata is much larger, if I rescale the system by the size, here's n is the number of streets, then you can see that pretty much all of these line up very neatly. So you have these bimodal, you have these two regimes. You have a regime here, which is kind of like here, and you have a regime beyond this peak, right? Furthermore, if I now not just account for the size, but I account for the shape, the fact that some cities are ellipsoid, some cities are long, some are ellipsoid. So a different kind of rescaling scale, then pretty much the distribution of congestion collapses onto one curve, right? So here are the steps. I look at the distribution of congestion of streets all over the world. I account for their size and I account for their shape. And if I do so, then I find that essentially it's identical pretty much everywhere. So whether you're in Kolkata, or whether you're in Lisbon, whether you're in Madrid, or you're in London, it's the exact same distribution of congestion. Once you account for these two effects, and you can actually calculate this analytically. So this dashed line is the analytical prediction of why that's the case. Why that's the case is not so much of interest, but it's a topological effect. It's a fact that it's embedded in two-dimensional space. I can talk about it if you're interested. But this doesn't really help us with the question that we asked, right? Can we use those congestion properties to distinguish between how these cities are different, right? How some of them are leveraging this effect, how some of them are not. Well, the answer actually lies not so much in the histogram, but in the spatial properties. So what we're showing here is the following. So this is a city in Spain, Santiago. This is their actual street network. Here is a random graph model of Santiago, random planar graph. These things that are outlined in red correspond to those streets which have the highest amount of congestion. So this is the top 10% of congestion. So you're going to see this filamentary structure. And in the real Santiago, these things highlighted in light colors is also the corresponding top 10%. And you can see this filamentary structure. Here you have what's called the edge density. And what this is the number of streets that are present in this space divided by the number of streets that can possibly represent the space. Right? So it's a matter of how dense the street network is. So this density is a control parameter. So as you can see, the 0.43 is a slightly less dense environment. And you can see that the high congestion areas have this tree-like filamentary structure. If I go to a place like Paris, which has a higher density of streets, and transition from this filamentary structure to something which looks more like a lattice-like structure, right? So you find that this thing, which is in the periphery, starts to coalesce, has a web-like thing, as you can see in Paris. And as I go to even more denser streets, this is Shenyang in China, you can see that that coalesces even further towards the center, right? So what's important to note is that the histogram, the distribution of congestion across all these three cities is exactly the same once you account for the shape and size, but the spatial properties of the high congestion areas is what's being determined, what's distinguishing between them. So in some sense, if you are building a very dense infrastructure, what you're doing is you're diverting all the congestion towards the center of the city. Once you divert the congestion towards the center of the city, that means you can't get from one part to the other because it's a barrier, right? You can't go from here to here, you have to go around, something like that, right? So the lesson over here is that you have to be very wise in how you choose the infrastructure. And it turns out that in those cities where you don't have this scaling effect, to a certain extent, not entirely, right? You do have this particular problem, right? Okay, fair enough. So the first step was the simple assertion that it's the interactions of people that's driving the scaling behavior. The second step was thinking about, all right, now what is it that mediates interactions? Now let's move on to say, okay, how is it that people are actually moving in this space? And then the question might be ridiculous in the first place because say, how can I possibly measure how people move? We all have free will. Yeah.
So your betweenness centrality is the measure of congestion. Okay? So that is irrespective of the human population. It's only the structure of the
Infrastructure.
streets.
Precisely.
Streets connectivity
Exactly.
in a particular
Exactly.
city or between two cities.
Exactly.
And you see that it follows the scaling.
Yeah. Exactly. Yeah. But then you can build traffic on top of it, and I can get to that later on. I mean, this will actually this builds on that. Okay. So this is an excellent question because at this point it's only in the streets. The question is how do people move on these streets? So how do you measure this? So a great but slightly controversial way to measure this is to use mobile phone data, right? And here are two examples of this. So this is from somewhere in some Western European country, you can't really name it. So this is the typical movement trajectories of two individuals over a period of a week or 24 hours. I'm not exactly sure, I forget. Either way, so what are we seeing over here? So the way this works is that, so now we're sitting here in SN Post Center and you make a phone call. You make a phone call, you have a cell phone tower somewhere nearby, right? So your phone pings that tower. Then you might go to city center, have a cup of coffee or something, you make a phone call, pings a different cell phone tower. Then you go to South Calcutta and so on and so forth. So as often as you do this, you're making a phone call that pings a cell phone tower. And then you do this for the entire day, you can project, you can retrace your steps. So that's what this is. So each of these cells correspond to a coverage area of a cell phone tower. This is a Warner decimation. So this is the center of the cells, and this is the number of phone calls. Right? Here's one user who looks like this, another user who looks like this. And you look at this picture, and it's a mess. It's like, how can I make any sense of this? It looks like a painting or something. So it turns out that if you ask the right question, it's very regular. So if you say that, let me measure how often do people move certain increments of distances. So let me look at all the people in this data set and I say, okay, what fraction of them move 1 kilometer? What fraction of them moves 2 kilometers? What fraction of them moves 50 kilometers? And so on and so forth. So this is again a histogram of displacements. That's what delta R is. Delta R is the displacement you have from your starting point, wherever you are, any given time. Any instantaneous displacement. So as you do this, you find that it actually is a very regular function. Right? It's a perfectly well-defined thing. If you fit it, you find that it's what's called a truncated Levy flight. So the probability of moving a certain distance goes as a distance to minus beta some exponent times some exponential cutoff with some characteristic cutoff. Okay. And like I said, so this is basically characteristic of what's called a Levy flight. A Levy flight is just a special type of random walk. Brownian motion is like, things just jiggling around with some constant, some small displacements. Levy flight is just Brownian motion, and then very occasionally you jump a very long distance, right? So, and it makes sense because most of the time you're driving around your neighborhood. Sometimes you go, I don't know, to Darjeeling, and sometimes you fly to, Rio, right? So that happens for air. That's Levy flight. The problem with this is that if you look at a theory of Levy flights, it makes a prediction. And the prediction is your mean square displacement, your characteristic movement as you go in time, it goes to infinity, right? But beta is data set dependent, and I think it's somewhere between minus 1.8 to 2.7.
This beta is not related to the first beta.
No. This is a completely separate beta. Yeah.
So this is not a flat Levy distribution with a flat tail.
What do you mean?
The second moving diverge. I mean, okay.
Yes. It doesn't take us. It's truncated, so it doesn't diverge. But if you remove this, it diverges. Yeah. So beta is in the it's a what is it? It's central limit here doesn't apply. So this predicts that you sort of move away to infinity, but we know that doesn't happen. We come back home every night, right? So it turns out that if you borrow this concept from mechanics, classical mechanics, or the radius of gyration, basically what is the characteristic movement? What's the distance of a center of mass with displacement? And that radius of gyration also follows like a similar kind of functional form, which is to say that the characteristic distance that most people move is very small distance, not very large, right? So again, without getting into the details, you can use a theory of continuous time random walks to combine this with this, and you can make the prediction. You can reconcile the fact that you have this truncated Levy flight and the mean square displacement by showing that in this particular case, if you combine these two, you have what's called ultra slow diffusion, which means the mean square displacement goes as a log of a log function. So it's an incredibly slow kind of movement, right? In Brownian motion, that goes as square root of t. In Levy flight, that goes as t to some exponent. But if you combine these two, you have this very ultra slow diffusion, which you actually find in glassy behaviors. If you're studying the Sinai model, is a one-dimensional thermally activated diffusion particle in some random energy landscape. There's the simplest model of glass. You also have ultra slow diffusion. You also see the same thing in directed polymers, right? So in some sense, human being movements are glassy and like directed polymers. Either way.
So whether this R square, you track a particular person and
Which one, sorry?
this last one, ultra slow diffusion. Or
This is averaged across the entire population.
So you track a particular person.
Yes, yes, indeed.
Over time.
Over time, exactly. Yeah.
While calculating the distribution, there can be two ways. Either just select one person and measure the distribution of it over the time, or for a fixed time for a large number of people.
Exactly.
Both will be give the same.
Both will be the exact same answer. Yeah. If you have large enough time and enough people, so obviously in the asymptotic limit, right?
So it means that gradually you are migrating over places. Right?
Yeah. I mean, it's not that surprising if you think about it, right? But what's interesting is you can quantify this. So,
What is the reason for this very long for your exponential cutoff?
yes. Exponential cutoff plus the radius of gyration. So essentially, it means that.
Radius of gyration,
So-
it seems this.
But so the thing is that there are two different regimes, right? So it's levy flight over a certain length scale, and then beyond that length scale, it basically is a short cutoff. So that short cutoff is what we mean this functional diffusion.
Maybe there is a center of attraction or both. That might be putting this so.
Yes, it is precisely because you tend to return to your wherever your habitual, where your habit. Right. Right. Otherwise there wouldn't be any reason. Like Paul Erdos, who never lived in one place but visited people, and worked with us. He might have a different. He never had a home. So what's interesting about this is that number one, you can quantify it, and once you have sort of these kind of these statistical properties, we kind of build generative models of this. You can start making predictions. However, I want to show you something which is a cautionary tale. So the problem with this mobile phone data, it's obvious. So first of all, you can only trace, you can only sample people's movements when they make a phone call. People are not making phone calls 24/7 a day, right? I make maybe one phone call in 3 weeks. So there's an issue of sampling. The other thing is that you are only getting instantaneous displacements, right? So right now I'm here, 2 hours later I'm in Golfing, where I just came from. What happened in between, I don't know. Right? So there's a lot of information that's missing. So you don't have information about velocities. You don't have information about how much time you spend in a place. You don't have information how much time it takes for a trip and so on and so forth. So another source is GPS data. So this is information that we had as the collaborators of people that I had in Italy and in Mallorca and Spain. So somehow they had access to about 2% of all vehicular traffic in Italy over a 1-month period, almost 1 million cars, for tens of millions of trips. And this is basically an insurance company. So when you sign up for an insurance company, they put a tracker on your car, and they measure your velocity, they measure how far you're going, how you stop, what's your braking rate. And if you're a good driver, you get better rates, right? So share this. So in addition to the displacements, you have not working, so this is fine. You have the displacements, you also have the velocities being, you have the rest time, how much time you spend in a location, and the travel times. The question is, with this additional information, can you actually do better? Do you get the same results, or do you get something more refined? So the first thing you can do is you can measure the travel times, which you never had before, right? So this is the vertical axis is the fraction of trips that takes a certain amount of time. So the time divided by time average, and this is across multiple cities. So it turns out that if you rescale this by the average travel time in each city, they all collapse into one curve. And this is semi-logarithmic scale, so that's an exponential distribution, right? So travel times are exponential. So most travel times are roughly about 1 hour or so. A few of them between 4 and 5 hours long term. So it turns out that one way to reproduce this exponential travel times is to have this very kind of simple model of random acceleration. So we just say that that my acceleration is just Brownian motion, just a random variable, coefficient, some white noise. So it's like saying I'm going, and then my acceleration is just completely sort of, which actually is a very good model for how people drive in. So, so you take the random acceleration and some other things, and what you can do is you reproduce the exponential travel time, and this model then has a prediction for the displacements as well as the average velocity. So the displacements that this model would predict, again, ostensibly looks similar, but it's not quite. So you can see that This beta is now less than 1, it's 3/4. And this cutoff is not just a cutoff, it has a power over here. So this is a stretched exponential. This is not a Levy flight with a truncated Levy flight. The prediction for the velocities was a square root of t. So when you actually measure the velocity as a function of time, this is the prediction of the model, the square root of t, but actually it's linear in time, right? So the model doesn't do pretty well. So it turns out that with a very simple modification, you can actually get this. Again, and I like this because you see with this tendency now of trying to do machine learning with everything and using these 7-layer neural networks, sometimes people forget that if you just sit down and think, you can actually explain these things a lot easier than doing these fancy kind of whatever. Anyway, that's a personal rant. So the idea over here is, if you think about a trip, you leave your house, you go on a slow velocity, you turn into your side street, your velocity increases, then you turn into the main street, velocity increases even further. Then perhaps you go to a highway, you reach your maximum velocity, then you take exit and you start going to your destination and your velocity decreases, right? So basically, in this model, if you have, you have the travel times from data, and you start somewhere and you have this, let's say, this fixed velocity increase. So you go up and you go down, right? You incorporate this into a particular model, and then you find that, again, with the exponential travel times, you recover the prediction that the velocity is linear in time, and you have a slightly more refined prediction for the displacements. And moreover, it actually tends to match reasonably well with the empirical measurements, right? So in this particular case, once again, you have an exponent alpha similar to that other exponent of the mobile phone data, which is a function of the velocities, and you have this stretched exponential cutoff. But really, all this is saying is that with two simple ideas, just looking at the travel times, or three ideas: travel times, a random acceleration model, and the observation that velocities are hierarchical, it goes up and goes down, I can pretty much reproduce the empirical observations. So I showed this for two reasons. So number one is that it shows the challenges of doing things like this, because number one, it's very data set dependent. You look at mobile phone data, you get one kind of result. You look at this GPS data, you get a second kind of result. They're not that different, but they're different enough. But the important thing is that you can quantify this kind of movement, and you can sort of have generative models to explain this movement, and therefore you can do things like prediction. These kind of things. Okay, so people's interactions, infrastructure, individual movement. What about collective movement? So this is a project that we had with Google, where we essentially had access to Google's Google Maps data, right? So this is basically about information about the movement of 300 million people worldwide across major countries, apart from China. Obviously aggregated, right, for the year 2016 to 2018. So the data that we have, because has to be anonymized, is basically saying that in the first week of 2016, 1,000 people went from SN Bose to city center. In the next week, it was about 500 people. The third week is about like 200 people, and so on and so forth. So you had some spatial resolution of about 2 kilometers square. That's how the entire world was divided up. And then you have the population flows between these different resolutions over the period of these 2 years, right? So this is cumulative movement. There is no data for individuals. So here's a representative example in the United States. Obviously, you scale out. You can see, sort of short-range trips in New York City and, of course, long-range trips. So what are the things that you can do with this? So one of the things that you can do with this is you can ask the question, is there any structure in these cities in terms of how people visit them, right? Which parts are the most visited? So what you can do is you can sort of like look at different parts of the city in this resolution. You look at the amount of people that come in, right? That's the inflow of volume. So how many people come into Salt Lake, for example? How many people come into Gulf Green, Korea Heart, et cetera, and then you can threshold, right? You can do these thresholding, saying these are the areas which are the most visited, these are the areas which are the second most visited, third most visited, and so on. Obviously, it's a function of what thresholding measure that we use. In this case, we use the measure of coherence curves. But basically, the idea is that can you extract parts of the city which are the most footfalls, right? So if you do that for a bunch of cities, so here's Paris, for example. See that Paris has like this dense red core. So this central part of Paris by far has the most amount of visitations from any other part of Paris. And then as you go to orange, that's the second most visited, and if you go to blue, is the third most visited, and so on. In other words, Paris has this shell-like structure. You go to Bangkok, you see that there is like a core, but there are different parts that are also equally visited.
Just remind me that what was red?
Red is the part of the city that has the most number of inflows. Right? So most number of people from all over the city. Right? So Bangkok, you have this core, but then you have like these different parts around it. And then if you go to Los Angeles, if you've been to LA, it's not a city; it's a collection of different cities. You can see that these visited places are pretty much spread evenly across the entire city. Right? So you have this centralized shell-like structure. There's like this raisin in a cake-like structure, right? The same thing from Alexandria and whatever, different types of so you can actually quantify this. This is nothing theoretical about this. This is a purely empirical study. So you can quantify this spatial structure by something which we call the flow hierarchy. So what this measures is, and I think the easiest way for me to explain this is in terms of actual cities. So imagine if I look at movement in India, and I find that people only move between Delhi, Bombay, Calcutta, and Madras, and people only move between Indore, Imphal, and Pune. Right? So all movement is between only tier 1 cities. So tier 1 people only visit tier 1 people. Tier 2 people only visit tier 2 people, and there's no mixing. Right? In that case, this measure that we have, this flow hierarchy, would be high, which means you are very concentrated, which means the majority of the movement in cities is concentrated only in the economic centers. Right? If that movement was more homogeneously distributed, so people equally visited Pune, Bombay, Calcutta, and so on and so forth, then that value would be low. So that's what this quantity phi is. And you find that, sort of like, as you go from the spatially sort of centralized cities to the more spread out, this value of phi pretty much goes down. Right? So that phi captures the spatial layout of these particular cities. You will see what is important a bit. Actually, it's quite important for COVID. You'll see in a second. But before that, I mean, again, this is a fun paper. I mean, it turns out that this I call it the dynamic structure of cities because really it's kind of a structure of movement of the population level, and it's kind of a low-dimensional proxy for all kinds of things that are happening. So it turns out, I mean, not to get too much of the details. It explains things like transportation patterns, pollution emissions, health indicators, all kinds of things can actually be captured by this one particular indicator. Right? Again, this is a purely empirical thing, but I want to show you how this can be used to study, like epidemic spread. So, which brings me to the epidemic spread.
Sorry, what was the indicator that you?
So this indicator. So this indicator is very high if all the population flow is only between the major attractions. So let's say only between
But I mean, it should have a independence. I mean, population. Or
all these flows are normalized by the total amount of flows.
just by
Not n, the total amount of flows. Yeah, so it's a function of it. The total amount of flow is a function. All movement. So they're all normalized. Okay. So far, like I've been giving you all these various descriptions of the urban center, and now I want to talk a little about how you can use these things, right? So don't have too much time, so I might just focus on this one itself. Epidemic spreading. So obviously, a topic of great importance. So how do people actually study these problems? So these predictions that you've been seeing over the last couple of years, people are saying, oh, here's a model that they've been using. It's an IIT model, which I get the news. The various models they've been using in the United States and so on and so forth. So really, what is the genesis of all this? So there are various ways of studying epidemics, but one way of doing this is what's called a metapopulation model. This pretty much comes from ecology. So the basic idea behind a metapopulation model is it's called a metapopulation because you split the difference between resolution, scale, structure, and ease of calculation. So what I mean by that is that imagine that I have these N patches, right? So again, this is Salt Lake, this is Gourab, this is Gulf Creek, this is Islay. Okay? And between each of them, there's movement of people, right? So that's where the structure is. But within Gourab, within Salt Lake, within Gulf Creek, you don't care about the structure. Within that patch, you have everyone has an equal likelihood of meeting everyone. So it's purely mean field. So there's no structure. Now you have a choice of how much resolution you want to get. You can make this as large as you want. You can make this as large as the city. This would be like Calcutta, Bangalore, Delhi, Chandigarh. Or it could be JD block, some other block, and whatever block. You can choose a resolution. Depends on the questions. But anyway, that's the basic idea. So you have these N patches, and within them you have some population. And there's a flow matrix, right? There's an exchange of population. Okay, so then how do I do this one step further? So what, yeah, someone say something? So one way to study this is what's called the movement interaction return model, right? So once again, we have our 4 patches, like I mentioned, you imagine people in the world, and in each of these areas, you have, let's say, there's 100 people here, 200 people here, and so on. Okay, now it's not that in every single area, everyone's always moving. Some people stay home, some people move, right? So what this parameter P of D is basically a probability of movement. So let's say what fraction of people in a certain area move from I to J or I to K or whatever it is. Then you have the flow matrices, right? So this is the fraction of people that move, and this is the exchange within different areas. So 30% of people might move from here, but it could be split between here, 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 and here. That's quantified by the flow matrix or IJ. Okay, so movement, interaction, return. So what happens? So in the beginning, people move, right? So I'm here in the morning, I go to work, here, so everyone moves, and they start mixing. And then depending on your epidemic model, let's say you're talking about the flu. Flu can be modeled by what's called an SIS model. In other words, you move around, and with some rate lambda, you infect somebody, right? At the same time, with some rate mu, you recover, right? So you go to work, and then you come back home, and the whole process stops. So the parameters of importance here are the number of people in each batch, the spatial resolution of the batch, the probability of movement, the flow matrices, and the epidemic parameters. Here you have the infection rate and the recovery rate. This is just for the flu. If I were to study COVID, there's about 47 parameters, right? So which becomes almost ridiculous. Anyway, so what I want to focus on is the effect of movement on how the epidemic actually sort of progresses. So here's a paper I did with some collaborators right before COVID, in fact. We were studying a hypothetical pandemic outbreak in the city of Cali in Colombia, where we had actual data for people and how they move and stuff like that. Anyway, what I want to show is the following. So here, so you have your compartmental model of epidemics, with just a set of differential equations. And one of the solutions for that is the fraction of people who are infected. So 8%, 20%, whatever it is. This is a fraction of people who are infected as a function of the infection rate. Okay? Now, if the infection rate is too small, you only have local infections. It doesn't take off. The infection rate has to be above some critical threshold such that the infection takes off. Right? So this is, if you look at these curves, you can see from critical phenomena, these looks very much like continuous setting on the phase transitions. And in fact, you can map this problem of the bond population exactly. It's the exact same problem. Right? Okay, so you have a critical value of lambda, and then you have a percolating cluster as well. That's your infection cluster. Each of these curves is what I want to show are colored by the probability of movement. Right? So blue means nobody moves. Everyone just stays in their location. 1 means that everyone is moving all over the place, and then you have intermediate values. What I want to focus is on 2 of these. If you look at this one, blue is PD equals 0, nobody moves. And you have a lambda, which is somewhere around 0.5, right? So the closer it is here, the worse it is. Then the easier it takes off. This is a situation where nobody moves, right? So you have complete lockdown. COVID comes, everyone stay in your home, nobody go out, right? Here's your infection rate, lambda. Here is the infection rate when you have 70% of people moving. And you can see it's actually higher. which means a situation where you have 70% of people moving between these locations is actually a better strategy to fight against a disease than just shut everyone down at home. And so there are some interesting reasons for this. This is true depending on the population distribution of people in a city. It's especially true when you have a more heterogeneous distribution. So in other words, if you have a dense population core and you have sort of less dense population areas, and I can talk about later on. Anyway, so you use this insight, and we looked at COVID-19, and the question, and we wanted this project before this thing actually happened. But what we realized is that based on a city's mobility patterns, the infrastructure, and so on and so forth, you can actually quantify how vulnerable they are to pandemics before a pandemic happens. Right? So here, what we're doing is the vertical axis is our predicted critical infection rate, right? So lambda critical is a point at which the infection takes off. This horizontal axis is that phi that I was talking about. Right? So these are cities on the right where most of the population flow is concentrated between the economic centers, like let's say only between Bombay and Delhi. And these are the cities where they're more evenly distributed, right? So again, the higher this is, the better. The lower this is, the worse. So what this is showing is that in those cities where you have most of the population flows happening only between these large population density areas are especially vulnerable to these kinds of pandemics taking up. So this is the prediction of our model and our analysis, and here's a validation. We did it in the United States for COVID post-hoc because that's where you had the most data for. And our model pretty much predicted that New York, I mean, it's kind of obvious, it's not really important, but New York would be the most vulnerable. This is a vulnerability index, and it was indeed the case. It had the lowest possible lambda critical you can extract from the infection curve. And although I'm not showing over here, there's another city called Atlanta, which is as big a center as New York, but its population density profile and the movement is much more distributed as opposed to centralized. And if you look at historically in 2020, it took a long time for the pandemic to take off in Atlanta. No one knew why. Right? So, okay. So here's a classic example of that. All right. So it's already been 55 minutes, right? So there's another thing that maybe I can talk about later. Let's skip this, right? So it's the prediction and information theory. So I'll just skip that. But hopefully, I've given you a flavor of of what people study in these urban systems, how physics can be particularly useful. And if you find this of interest, then we wrote this review paper about like 4 years ago called Human Mobility Models and Applications, which pretty much covers most of these things. It covers like the data sources that people use, the theoretical models that people use for stuff. What are the future directions? What are the interesting questions? It's about like 120 pages, right? So there's enough information here if you so choose to read. And I would love to get some feedback on this. So I just want to thank my collaborators from Zaragoza parts of the world, but more really my group. So this is Hugo Barbosa, who was my postdoc, who really helped me in many of these things and setting up my lab in the first place. He was now a professor at the University of Exeter. Surendra and Sayath just recently graduated with their PhDs. They decided to make money instead of paying the academics. Being a scientist. Kristen just joined the CDC right before COVID. Brian is now professor of liberal arts college, and then some undergrads, Shiva, who's now on finance, and of course, perhaps my most talented student, Alec Berkeley, who's my undergraduate. I was a professor at the University of Hong Kong, straight from PhD, without being a postdoc. If you are interested in the kind of things that we do in our lab, then please feel free to go to our lab website. I also tweet at Ghosal G, where I just mostly post some of my papers and stuff. And I must plug, we are always looking for very talented students like you for postdoc or research or visitors. So if you're interested in the University of Rochester, please feel free to reach out to me, questions and whatnot. Love to have live. So with that, thank you very much for your attention.
Okay, thank you so much. Gourab, and now we are taking it now open for questions, comments.
I have a question. I mean, this mobility, you are in the discussion. Now, there was this convergence economic model that, between the two cities, gravity model. But that requires the the population of the city and the other city, and of course, maybe inversely proportional to some kind of link distance or something.
Yeah, yeah.
So, but you do not see, I mean, you see only one population. I mean, that's from the city where from the persons are going.
No. We can look at this from different cities. So the first thing is that the gravity model was first proposed by Ravenstein in the 1950s. The gravity model pretty much says that the expected flow between two cities is a product of the populations of two cities and an inverse function of the distance. It would be like r squared or whatever. So it's been shown that the gravity model is not a very good model of what actually happens. Because if you look at the empirical flows,
But there are some,
for instance,
recent review on this in the trade structure between countries still has some. I mean, of course, now the differences have to be redefined on the network.
yeah. Exactly. So these flows are empirical flows, right? So the gravity model would then tell you that if I take the population here and the distance between these two centers, and I can predict what the flow between these two are. So it turns out that yes, it's not really a function of distance actually. It's more a function of something what's called an intervening opportunities model, which means that the population flow between two areas is not so much a function of the distance, especially now with transportation and stuff like that, but more a function of how many economic opportunities are there before I go from one part to the other. So that's actually a better approximation. So yes, in the analysis that I have presented so far, I've only looked within cities, right? But I can use the gravity model, for instance, to say, okay, I predict the number of flows from Salt Lake to Gulf, the population here in Salt Lake. But I didn't need to use a model simply because I had the actual empirical data. If I were to try and fit the gravity model to that, it would not be a very good. So they're better. I don't know if I answered your question.
But yeah, I think they define now the distance in a with opportunity and all this.
Yeah.
Anyway, that's the redefined definition of a distance, and then that. But they make it quantitative. I mean, I found that it's interesting to try again that.
No, absolutely.
One thing I mean, the first paper that you showed, Helving and others, I mean, the first paper that you.
Yeah.
The first paper. Yeah. But Helving is also there.
Yeah, absolutely.
Yeah, so they had some indicators. I mean, can you just go back to
Sure.
that? I mean,
This one, right? Yeah.
now, in some kind of maybe social indicators, again, it is proportional to the city N, I mean, mass or whatever, population. And then it grows with time, that is a different thing. Now, you see that one important indicators of in our academic life is the Harsh index. We all have that. And it is, there is an analytic proof, not very accurate, but it's a good conjecture, that the Harsh index is proportional to the number of papers, typically. You have to write thousands of them.
Yeah.
And square root of that.
The geometric mean of the papers.
Yes, in a sense, it is square root, not n.
Yeah.
It's interesting, and also number of citations, total number of citations also, that is very accurately checked. What we tried is, you can define Harsh index for population clusters.
Yeah.
You define particular size to get the Harsh index, and the clusters have different size.
Yeah.
So that's their kind of citation.
Yeah.
And then you can measure the Harsh index.
Yeah.
It indeed goes as square root of that.
Really? Oh, yeah, okay. I know the people who do the geometric mean, they're friends of mine. It was
So
very
now
nice.
I wonder whether these indicators, like GDP and others, whether they are really going with n, or you're saying that even n log n. But there is one indication that it is square root of n by log. So it is, first thing is forget about log n. First thing, it is not 1. It is half. And for Harsh index, it is almost exact. It is not
I don't know. So the thing is that
1.5.
No, no.
Lot of different.
Yes, that's right. I
Yeah,
mean,
so,
the thing is,
so there are things that go at half. So, I mean, so I'm not showing the whole thing. So this is the set of things that goes as greater than 1. There's a whole set
no,
of.
I mean, I'm not talking of T. Dependent. No,
Right.
with time that will be something.
Well, I'm saying, so this is
N to the
into the beta, right? So I'm saying that here,
Yes. Oh, it is
Is it
N to the
NT?
power beta.
into the power beta, sorry.
Oh, I see.
Is
Oh,
the NT n as a function of T and a whole
and that
to the
is
power
so
beta?
small. No, that is still one point something.
Yeah, 1 point something.
Oh, so it is already into the
Yeah, yeah,
more than.
yeah, yeah.
And Arts index is clearly not.
square root of it, yeah.
Um,
But what I'm saying is that here, so I've shown some things, so I've shown a class of things which goes as beta less than 1. And then everything else, like for example, length of roads, city size, uh, electrical lines, I think, like electrical lines, they all go as square root of it. Because you have economy of scale, right? So at some point, you don't have to, there's a limit in how much electrical lines you can lay, which will give you electricity. So they go as square root of it. So anything spatial goes as square root of it, or less than half. Anything like this goes. So there are two universal differences, yeah.
Arts index false. I mean, why? But it works in physical systems.
That's very interesting about the population clusters. Yeah, yeah, yeah.
So should we go to the next?
Sure, sure.
This relation that you have shown from the data, IT goes as NG to the beta. Is it true for in what is the typical time dependence of N? Does it go exponentially? NT, how does NT depends on T? What is
Sigmoidal. NT pretty much, I think, as initial exponential growth and it saturates. I think as a state.
NT is the number of, is the population within a city.
Yeah, so it increases exponentially, then it saturates. The sigmoidal growth.
So the then one question arises, is data for how many decades of N? I mean, see, I mean, of course.
This is just a snapshot. Just to get like for one.
No, but we have
Decades you can read from here.
One can see it.
Oh, you mean like the this?
Right,
Okay.
I mean, yeah.
So I was again. This was something which was stimulating the conversation right at the time, 2013. So there have been several papers that have been written over the last 9-10 years. That really questioned this.
No, but this time scale, what is the time scale? 100 years? 1000 years?
So that's what I'm saying. That question. The question is how robust is this thing actually? And it's all entirely clear because there have been evidence for and evidence against. And as you said, exactly like what you have is only an instantaneous snapshot of time. So what you want to see is the actual evolution of the city from beginning, like beginning of Rome to now, right? So again, so I wouldn't take this that seriously, but this was a good starting point.
No, but again, quite, I found it quite surprising. Maybe not that surprising, super linear. So it means that for example, it's a crime rate. So then it means that crime rate actually increasing over time. I mean, you go larger population, crime rate is also increasing. That's bad news. But if you see at the GDP, I mean, production rate is also increasing. That's a good news. So there is operativity in the system. And I don't know how to exactly model this. I mean, you said something. But it actually indicates cooperativity. And there we are cooperative in nature. So,
It basically indicates a multiplicative effect, right? So
Right,
whether you're a
right.
positive thing or a negative thing. But again, I mean, I wouldn't take the values of this too seriously. Just the
so how do you measure crime
But this is
rate?
greater than 1. That you should take
it's
seriously.
greater than 1 for sure. Yeah. But I wouldn't take this the number seriously.
So that's the point.
Police
the
report, yeah.
last part of the talk where you correlate on different nodal things like connecting the two blocks or connecting different cities? Are there some self-similarity, like I connect different country or connect different city? Are they all belonging will give the same result or will be different?
Which one?
Like you said, like suppose I connect different blocks in the Kolkata, like suppose in South Bay. I connect
Yeah,
different
this one.
cities.
This one?
Or if I connect different countries, all the results will be same, or is there some common nature, or if they have the same kind of structure that there is a one central point in each.
Irrespective of the resolution.
That's what yeah, suppose
Yeah.
what resolution I can see. I cannot see inside a house, obviously.
No, I don't think so. Well, it depends, right? So I mean, it's like saying you're almost saying that I'm renormalizing the system, and then I want to look at the running of the coupling of like the infection rates and the recovery rates, right? I'm not so sure. At least for this case, it doesn't work because I mean, the the actual epidemic dynamics is so complicated. I don't think it's that simple to extrapolate from saying that okay, here's the infection profile in Calcutta, and then that can be extrapolated to West Bengal, and then that can be extrapolated to India. I don't think so. In terms of dynamics, in terms of structure, yes. And there people have done this. I mean, they have done like these real space normalization proof analysis of spoken
You're saying for the epidemic, it cannot, but otherwise.
Otherwise, yeah, there's still some good happening.
You also mentioned different lambda values for New York and Atlanta City.
Yeah.
So that means that there is a lot of inhomogeneity.
Yes.
So that is actually an argument against self-similarity.
So
Exactly.
because
No,
the
I'm talking about
cities have
the.
a different structure.
I'm talking about the.
You said the
I'm
same
saying
Yeah,
they
thing.
have the same structure.
Yeah. Exactly, because I mean, Atlanta and New York are very similar in the macro sense. The distribution of the population that flows are very different. So Atlanta, the pandemic took like 7-8 months to take off. In New York, it was like 2 weeks, almost.
Any other question? If not, let us thank Professor Ghosal once again.